Cover section 2.3, 2.4, that'll be brief. So I do want to point out, you'll find that this will be really quick. And then we'll cover section 2.5. So we're like, okay, well what's 2.3? 2.3 is using the limit laws. The limit laws to evaluate a limit. Well, I'm going to write that another way. Use the limit laws to evaluate a limit. Okay, how about, you can just say, finding limits algebraically. That's probably a better way to think about it. Finding limits algebraically. Maybe that's a better title. So today we do algebra. Probably more so than the other. We do a lot of algebra and calculus. But it's simplifying. Every type of simplification you ever did in an algebra class will probably come into play today. 2.4, what's that title? Well, that's the precise definition of limit. That'll be brief. It's the precise definition of limit. Like, how do you really define the word limit? As precisely as possible, what do we do? That won't be too far. And then this 2.5, that's just on continuity. So I'll put that here. 2.5 will be continuity. Continuity and 2.5. So that's what we'll be covering today. 2, 3, 2, 4, 2, 5. Anybody have questions? 2, 1, 2, 2. Any textbook problem? You got one?
Number 11.
Which section?
2.2.
So I went in 2.2. Let's go to 111. Oh man, you're the best.
Alright.
I love that one. That one. I didn't do this problem last class. I'm so glad you brought this up. So we'll definitely emphasize that one. This was from 2.2, and this was a Professor Mestre. You forgot to do one like this. Of all the problems we did, this thing is a piecewise function. So they got f of x equals, I got the squiggly symbol, right? The little brace. They got 3 parts to this. There's a 1 plus x. They got an x squared. And then they got a 2 minus x. Then they've got if statements. If x is less than -1 is this part. For the x squared, they got if x is between a -1 but less than a 1. So between -1 and 1, including the -1. And then for the 2 minus x, they just got if x is greater than equal to a 2. Oh, it should be a 1, I apologize. Alright, if you want to put little commas here, you can. Little commas. So, this piecewise function, or piecewise defined function, it's 1 plus x here, it's x squared here, it's 2 minus x here, and after all that writing, they go sketch the graph of the function, use it to determine the values of a for which the limit exists. Alright? So we're going to define which values of a for which the limit exists. What we're going to do is, this is how I like to design this on tests. Use these functions that exist everywhere, but we have to really check on this what? -1 and this 1, right? The critical numbers to see, is the limit existing if there's 2 numbers? So the way I'll word the question is basically the opposite. Can we define where the limit does not exist? Does that sound good? We're going to focus on that. Where does the limit not exist? But to get this going, what's an easy way to do this? Make a graph. So let's go ahead and make a graph of this. So let me just write this down. And when you and I have to find the x values, at which f of x is not continuous. There's another word for not continuous. You can just call it discontinuous. So I'll write that. Discontinuous. Right? For which the limit does not what? We haven't gotten continuity yet. I'll do that at the end of class. Find the answer which f of x does not have a limit existing. And I mean a 2-sided limit. write this word limit existing? We're going to find the answer at which f(x) does not have a limit existing. Well, when you all know about y equals 1 plus x, that's a straight line, right? That's going to be safe everywhere. X squared is safe everywhere. That's a parabola, right? 2 minus x, that's another straight line. So do y'all agree we got 2 straight lines and a little parabola? Great. We're trying to focus on what's going on at what? -1 and what's the other one? 1. If we had to guess, we could just guess, okay, it's discontinuous at -1 and 1, you know? We'd be close. True. But we got to check these out. So one way to do it is graphical. We can make the graph. So let's graph this thing. It's not as bad as you think. We'll make this sketch. Let's start with that straight line, right? That's a straight line. I got to do it on x less than -1. But it doesn't have an equal sign. I still need you to plug that in to make that line. So if you want, you can just make a little table. Right? You plug -1 in there, what do you get? 0? Yep. All right, give me one more value to plug in that so we can make a line, but go lower than -1. I use -2? Just to get the graph going. So I mean a little table, I'm just going to sketch that little line right there. I'll use -2. 1 plus -2 is what? Yep, 1 plus -1. So let's sketch that. At -1, it was 0. Alright. At -2, it was -1. Right there. Ah, negative slope, right? Or excuse me, positive slope. Going up from left to right. And there it goes. Hey, does anybody know why I'm keeping an open circle here? Does anybody know why I kept this little point open? It's because it didn't have the what? Equal symbol. So I kept an open circle there. Yep. And this is your x-axis, that's your y-axis. One piece done, we just need 2 more pieces, right? Alright, parabola. Well, that's easy, x squared. Yeah, but still, let's make a little table. X, y. What 2 numbers should we plug in? Plug in a -1, see what you get. Plug in a little 1. That way we can just make the sketch. Just want to make a little sketch from -1 to 1, right? -1 squared is? 1 squared is? Ah, cool, that was easy. Which one's going to be open now? That side I'm going to close dot it. This side I'm going to, yep, so I'm going to keep this side open. All right. So at -1, it's a 1. Okay? Close dot. But at 1, I got to keep this open. It's going to be a positive 1 like that. But a parabola does a little hook, doesn't it? Almost done. Hey, I bet you already know one of the answers to this question from what we have so far. Can you all spot it? At which value do we already know it doesn't exist? The limit. Remember for limits, the left-sided limit has to equal the right-sided limit. And what I'm saying there, Chloe or Colin, is like, when we look at these graphs, as I approach -1 from the left side, the number it's got to match is the number it approaches from the right side. And we can see they're not going to the same spot. So the limit definitely, we're going to write it down, the limit definitely does not exist at -1. But now we got to check 1. So we'll finish the graph. Everyone okay on those 2 pieces? All right, one more piece. Plug in a couple points into that guy. Make a little table. All right, let's plug in a 1. And then we'll plug in a 2. 2 minus 1 is 1. 2 minus 2 is 0. And close dot it, right? Okay. And I'm going to plot this point first. There's the 2, 0. Notice what's happening here. I'm plugging 1, 1 where there was an open circle. So what happens to the open circle? It gets closed up. That's right. See that open circle that I had before? It gets closed up. It just got closed up. Aha, the graph is, we'll get to that later today. The graph's continuous. Continuity, the graph's continuous here. It's not continuous there. So everyone, let's go on -1, limit does not exist. How about at 1 now? Well, does the graph approach the same value from the left as it approaches from the right? Yeah. Cool. Do you see that, Chloe? It's like, oh cool, it's like, look, as you approach 1 from the left, you're approaching a 1. As you approach 1 from the right, you're approaching a 1. So the limit exists at 1, but the limit does not exist at -1. So the answer to this question, find the x values at which f(x) does not have a limit existing at x equal to -1. Hey, make a note, on your test, we don't meet Monday, but next Tuesday. I'll have a problem when you gotta do something like this, but it's gonna do with continuity. It's gonna be continuity, and you go, oh, but it's gonna be basically the same thing, you wanna make a sketch. Continuous is easy, just think connected. Find where the graph's connected. If it's not connected, it's not continuous. You know, we'll get to that later, we'll define it, we'll make a nice, nice precise definition of continuity, but just look to see where it's not connected. Where is it not continuous? So that you already have a sense of 2.5. It's not continuous at what? -1. Where is it continuous? Everywhere else, right? Same thing with limits. Where do the limits, now you go back to that question the book asked? The limit exists everywhere except for what? Everywhere except for -1. That was a good one. Thank you for bringing that up. I meant to do that one. I did. Hey, any others? So we definitely should do another one of these in 2.5, everyone. So let's come back to another one of these in 2.5. Cool. Hey, any other questions? All right. Hey, so we're going to hit it. Everyone, we're using the limit laws to evaluate a limit. Where are the limit laws? I mean, you like reading math textbooks? They've got them all listed. You go to page 99. Flip over to page 100. Get on to page 101. And when you'll see 11 limit laws. So what are you memorizing and stuff? I don't know. I think let's just jump into the lesson here, and I think you'll find that you can be okay with all those limit laws. Seriously, you can read through them. But the whole idea, this idea of finding limits algebraically is all these problems in 2.3, everyone, you're going to notice, deal with two-sided limits. Okay? And we're going to find the limit algebraically. So use the limit law to evaluate a limit. Well, how about this? Let's find the limits algebraically. But all these questions you're going to deal with, at least the majority of them, are going to be two-sided limit questions. Sound good? What if you have to do a one-sided limit problem? I just want to point that out first. Just be a hammer. You're going to find one-sided limit problems. What's the best way to do it? I don't recommend algebraically. What's two good ways to do it? One way is graph, right? These are my recommendations. Graphically. But what was the way we introduced right at the end of class last time? Tables, which is numerically. You can use either word, just try. So these are my recommendations. If you have to find a one-sided limit of an expression, and I say, well, look at the graph, it'll tell you the story, right? But also you can try it numerically. That's where you plug in numbers, like he said, a table. You plug in numbers really, really, really close to that endpoint to see what's going on there. And you'll find out what's going on with the one-sided limits. But what if you got these two-sided limit questions, like this? I'm going to start out. 2.3. We're going to do a limit problem. All right, when you got to find this, find the limit. As x approaches 2, x squared plus 3. I have a feeling you might like this section. So that's a two-sided limit, right? Well, now there are three ways to find limits. Graphically, numerically with tables. You can do it algebraically. I think you're going to prefer algebraically. Because you simply do what? You just plug it in. That's what you do. I mean, you can make the graph. You can look to see what's going on too, but that's what you're going to get. Cool? Just plug it in there. That's what we'll do. We haven't read through those in 11 limit laws, but we get that. Plug in 2, what do you get? What's 2 squared plus 3? You go, it's that simple. Are you serious? That's the end of the lesson 2.3. We're like, no. There's got to be some what? Weird scenarios, and we'll get to that. But I do want to point out, that's what you do. You got an algebraic expression, like I can just substitute 2. Get it? Because it's two-sided limit, I've got an algebraic expression, it's always safe. Well, what's the scenarios we really got to focus on today? Oh, you bet, fractions, right? Is that what you're going to say? Fractions. And in mathematics, when you get these fractional expressions, they call them rational expressions. So you're going to get a lot of rational expressions today. I want to make sure you're an expert. Okay, I want to put a lot of, they call them rational, sometimes they got radicals in there, and if it's got a radical in there, it's not rational, but it's still a fraction. Well, the key is in math, I'm going to put 3 numbers up here. Whoops. What's that number? 0. That's 0. So I do want to point out that if you plug in the numbers like we just did, and you get 0 over 7, then your limit is 0. Cool. Here it's not though. What's going on here?
It's another number.
Non-existent, it's not a number. So if you get a value like this as your answer, then you're just going to say the two-side limit does not exist, it's non-existent. So what's the third scenario? Okay, let's go spend the next hour on this scenario. Because you'll get this, piece of cake. Like I said, it's like we can move on to the next section. This is the scenario we got to look at. That's called indeterminate form. Indeterminate form. Mathematicians went crazy with this form. Seriously, they just kept going, figuring out neat ways to solve limit problems when you get what's called indeterminate form. If you plug in that number, like we said, substitute the number into the algebraic expression. But if you get 0 to 0, then don't stop, keep going. So we got that? Don't stop and say the answer is 0 because it isn't. The limit may exist. You'll keep going. So indeterminate form means you can't determine the answer right now. You got to do something to the expression. And you go, what do? We've used every tool we've used in our whole algebraic experience of our life. And we bring it into play. And we try to mess with it. We try to algebraically manipulate the expression. Okay? So if your algebra is kind of like what right now? Then let's do some review on some of these problems. Everyone okay with factoring? You'll see some factoring. You want to know how to add two fractions that the denominators aren't the same? You need a common what? No. Common denominator. Okay, we know that. Anybody in here ever multiplied a conjugate before? All right, you might have been a while, so we might do that too. We're going to use all these little tricks so that we can manipulate something if we get this. We can manipulate the expression, then substitute the number, and see if we get the answer. Sound cool? These methods of graphing it still work. You can still pull out a graphing tool and graph it if you want to investigate it. Sometimes it's hard, you know, it's hard to see what that limit is, especially if it's irrational. So, here's my first one. All right, I want to find the limit